Today I'll show you the conceptual mathematics about hallucination. I think many of you seen my lecture before, so you know how this works. For those of you who have not, so I like to teach in Excel, and I wanted to think of it as a really big whiteboard because I can sketch on this. I have unlimited amount of space on this whiteboard. I'm just going to talk about the first section, agent hallucination. Imagine you are the AI engineer trying to fix hallucination for your agent, and then you will be reading this. This is an example of a a log between user and the agent. So, for instance, user will say summarize the 2024 NVIDIA earning reports. Then you get this paragraph, and then from the agent, and it sounds very convincing, perfect grammar, and lots of useful information. Even says that it has verified the result. But then if they are hallucination, what kind of hallucination? Where can hallucination come from? So let's think about this a little bit. So, for instance, if you think about this, okay, citing the resource according to the retreat report for NVIDIA earning. So this document is going to store usually in the database as part of the RAG. Maybe this data document doesn't even exist. So this could be a RAG hallucination. And then you're going to use about 75 billion. So this is a number, a some number over here. And is this true? Is this actually from the data or actually from large language model? They might have seen this number in relationship with NVIDIA somewhere else, but the number is actually incorrect. This doesn't correspond to report. And then on the agent side, and you can see that, oh, obviously it's trying to verify stuff. So maybe the agent, when you develop the agent, you told the agent you'd like to be like thorough, or maybe you want the agent to double check everything. So it's going to, then you see evidence that it's trying to verify this result by actually looked up this API. And so this is actually a tool that the agent is using. So you can say, okay, this is connected to a tool. But does this tool really exist? Could there be maybe the tool doesn't exist at all? So we might have to check whether there's hallucination there. And then it's trying to confirm the same figure. And there are some other component of agent. The agent remembered your previous question. You're trying to make a plan to answer this question. For instance, in this case, it seems like they follow a plan that will retrieve the report here, also verify using API. And then maybe the third step is that we're trying to connect to the recent news with Tesla to develop 5 nanometer optical GPU. And optical GPU doesn't even exist. So it might come from LLM. So this is an example of manually analyzing various logic that are involved in hallucination, where hallucination can happen at multiple levels. Could be LLM, can be RAG, can be one of the components of the agent. So I just started with this example to motivate the rest of the lecture that have different aspects of hallucination we can discuss, and then where they might come from. And as typical of my lecture, I want to take you deep into the black box. I'll have you do some calculations as well, and feel free to follow. So anyway, so let's go over just give you some flavor of mitigation strategies. That there's quite a few now, but I picked 3 that we could practice and do it by hand, and you get to emulate the process how one would develop a mitigation system algorithm into your agentic framework. So first is technique I thought is pretty cool. It's called self-consistency check. That people discovered that if you use the same prompt, try once, try twice, try 3 times, and then you look at the responses, and then you compare them, you realize, hey, most of them are exactly identical, except these numbers are different. So there is one phenomenon people studied observed that if they say different things, maybe this is very likely to be a source hallucination. So it's called a self-consistency check. You will use the same prompt multiple times, and they will just, if the things that seem very different, that could be the part that hallucination happen. And it's like my kids. If I ask my kids, did you do your homework? They say, oh yeah, I did. I did it last at school. and ask the person, my kid again, did you do homework? Oh, yes, I did with my friend. And I started to see this inconsistency that could be my kids are hallucinating about whether he did the homework or not, right? So this is the concept. And then later on in today, we're also gonna go into the math, why it is the case. What is the math behind this phenomenon? So there's an explanation about that, and the way we can fix it, hallucination at that mathematical level. Okay, so there's one very simple, quick win about hallucination detection, basically by checking for self-consistency. And the second is that with also very straightforward is tool verification. That one of the major source of hallucination is that it just make that tool that did not exist. So the way that we actually check for this, actually I cannot click on this for some reason. What happened here? All right, let me just fix it. So if I cannot click on this, I will be able to edit. Then okay, give me a second. Maybe I just use my mouse. Okay, here. So we will have a tool registry that you know that you do have these tools. They're available, and it is what the typical tool registry looks like. Has a name of tool, you have some purposes, and you also have input and output. And you give this information to make it available for your agent. When your agent is engaging large language model, the reason they can pick the right tool actually from this list. So because if you have that, and then you could go into your log and to see that if your agent log like this, and go scroll down a little bit, and then. And these are the example of the, I say there's 10 different tool attempts. You can analyze the timestamp, and these are the tool call, and these are parameters that agent decided to use. And so this is an example of how what goes through this. Is it grounded? If this one, meaning that you can find web.search in our table over here, web.search. And if you have a 0, so is there a finance, lookup earnings, and it's not grounded because it doesn't exist in your table. And it could be a simple, I actually have an equation here to show you that how it can be done. Wait, I cannot access the equation for some reason. All right, you bear with me. I think I'm gonna close the Excel and reopen it just to hopefully this problem will go away. And then let me see. Give me 1 second. Come up. All right. This is what I need. Okay. Okay, then my mouse is back. Okay, cool. All right. So I actually do use an equation to do this. For instance, I would do, this is the equation I did. Count if this has this number. So what does it mean? I mean, I will count if the range is that all the tools I have here has that comma and has this particular tool that I recorded in the agent log. If the count is equal to 0, so this would mean that hey, there's a tool hallucination right here. Okay, so this, if we put it this way, it's actually not that hard. You add another layer of logic in your code. You can write Python code to analyze your log to do that. And then this is 1 because this search events tool actually exists. And the third is also popular is that I wrote the program to do this, but sometimes the logic could be more involved. So this is another popular way to do. What if we just use another LLM that's more powerful, and to also analyze this log? And so this is called LLM as a judge. And as a judge, you usually involve a judge prompt. So this is an example of judge prompt. Like, oh, there's a ground. We have models answer here. So this is a sentence that from the earlier example. And then in our prompt, we'll say, hey, in our training, maybe we do have access, a human expert way to look at this. So this is a human expert. And so during the evaluation time, then you say, judge, can you judge whether your factual consistency, identity, if the model's answer included hallucination content, and respond with this. And what do we do with this? We actually take this whole prompt and to give it to the model, to LLM. I want to emulate. I like to use the Excel to emulate the computation that so you could internalize the process. You write your lane chain or lane code to do it. So you will send this to a model. So in this case, the way I sent the model, I decided to try Gemini. So I use copy and paste to actually simulate the process. I copy and paste. Actually, what did I? So let me just say, how can I copy and paste? Copy and paste. Fail. Go back one more time. I should copy and then paste. I don't want to paste image. How do I paste not image? Just text. Can I just copy text, please? Let me do this. Paste as plain text, okay? And delete the image. And this a model is going to give this answer like this. So I will just copy this answer back to my result. So this is and then your evaluation hallucination detector, they will be able to use this. Just paste this. So this is the JSON the hallucination detector can use, except that I kind of didn't leave enough space. So I'm going to just undo, only copy maybe just the beginning a little bit. So make this example work. So this is the exercise I'm gonna do a few times to simulate the process of how the agent will work by where the large language model. Whenever we have to engage large language model, so I'm going to do this copy and paste to an actual large language model in live to illustrate this process. So these are just 3 different ways at the agent level, and then some very straightforward, self-consistency and verification, and also LLM as a judge. In fact, it's just a big prompt, and you take part of the answer and to another large language model to determine whether it's hallucination. All right. So this is just 3 to give you a flavor, but what I want to really get into is to some of the more interesting part. I don't know why I have all this. I just erase all this little ugly links. Okay, so now I want to give a quick overview of going back deeper to show you what does it mean? How do we evolve over the past couple of years? So we evolved from LLM. When ChatGPT came out, everybody started to talk about LLM, GPT, and was a very difficult word to say. And now we can all say it. So within a few years. And last year, everybody talked about RAG. And this year, everybody talked about agent. How does it evolve evolution? So I prepared this to show you the incremental evolution and trying to highlight the core concept of these 3 things. The first is that study with LLM. So when we started to interact with the large language model, it's quite simple. We we have a user input say how much are apples. So we use that from this. We might take this from the user interface and then we'll generate a prompt. And the prompt could be as easy as I don't need Chinese. Come on. It's not okay. Can I have English keyboard? Okay, cool. So I would basically just pass the inference. I use equal sign and just select my user input here. So this is my user input as a prompt. And I'll just paste it as is to large language model. And again, I'm gonna emulate my large language model by copy and paste to my Google Gemini and paste plain text. And so this is how we used to do in the beginning when language models came out, and people started to realize, hey, this language model are quite verbose. They tell you a whole bunch of stuff. And then, so this is a problem. And then you start to do things like, oh, be short, just answer me 1 sentence and add a bit more to your prompt. So this is and then sometimes it's not really relevant to your information. For instance, this tell you all this information about different brand and that, but then might not be related to your particular country. So this number could be very different from different region of the world. So that's when we move to RAG. We like the responses. So I just do it. Copy all these responses here so we can compare later. So for instance, I just copy this response and then copy and back to so you can practice this back to the response. I copy here and paste here. So this is the response. A lot of stuff is information, but might not be relevant. And RAG is invention people started to do, including Vectera many years ago, that before everybody else started to invest in building this system. The idea is that, hey, perhaps to answer how much are apples, we would like to provide some more contextual information and more relevant to my context, for instance, a particular store I run. So if you have your own store, you have your own database that with all the information about your pricing, for instance, your grocery. So that And the process goes like this now. So with the prompt, you say equals user input. The switch, this part is the same. But so previously, we just gave this input to LLM, but right now, we'll give this input to our database first. For instance, how much an apple? I can do the keyword searching. So I'll do a keyword. Apples is my keyword. Apples, this keyword. I have this code. I could emulate my search. So actually use apple with singular. Go back to my keyword apple, and then look at this result. There's a file or database. This is very cruel, a very crude emulation of database search. So I get this information: apple, Fuji, Gala, 2 different breed, and the price per pound. So we select these 2 rows in our database. Okay, and then once we have that, so I could just copy the database, inject this database search result into my context, and then it will take this whole thing to how much are apples to my large language model, and which I'm going to simulate by, again, Gemini. Paste this and paste. So not that, like that. Paste and in plain text. Oh, come on. I paste as text, and then you'll get a new response. So this is how RAG work. So now going to the generation, but the generation is a bit more, it's still kind of verbose. And so we might add a system prompt to be brief or be short later. But this is an example. Now this answer is more relevant to your result. Okay, so it's called RAG. And now I paste my response. So this is, again, I like this exercise because you manually emulate by hand how the RAG system works. And this example I use a lot in my class to compare between how LLM and RAG different. And next, we can evolve to the agent side. So we have this still database, but we still have a first interaction. Erase this. And that's how much apple. So what's new here is agent have these 2 things: tools and rule. Something I will like to add. And tool is, it will have, so in fact, earlier in the RAG, when we retrieve from database, it's just one application, but for tool, you can have actually, what if we can do something else? Look up web search over a coupon calculator. So you code this agent by telling the agent that you have registered this. All you can do. And with the system, maybe I could be something like, so pick a tool. So this is my system prompt. So pick the right tool, and with a role that in earlier, or just assume that user want to look up. But if you are coming from the building this for a grocery store, maybe you like to do something like, I want to offer you promotion. I want to be a promotion representative. Okay, so you can type role like this, and the prompt will be the same as your user input. So this part is the same, and context is no context yet. So right now is the first interaction. But what's interesting is that you could still give this to large language model, and the model is going to use this information and actually do, I'm gonna pick a tool. So I tested it with Gemini. It seemed to work. So to emulate this process. So this is how okay, come on, I keep doing this. Go back, copy, and paste as plain text. So this is how we emulate how the agent actually works. So they give this to the underlying language model. You can say, hey, so you will say pick a tool. Okay, say too much. Okay, does it say? Oh, this is really not great. So it say too much. Maybe I will say pick a tool, and just say the tool name. So so this is a way, sometimes you develop agent, this experience is kind of like this. And then I'll take this again and paste it to Gemini. You could try a different model. I just want to do Gemini today because I don't use Gemini much. So it doesn't have my memory. So, okay, web search. You said web search. Okay. All right. So I was hoping that when I was testing it, it says it's gonna say offer the coupon. So just imagine that it says offer the coupon for my example to work. So large language model just say, hey, I'm going to offer the coupon. So that's why the example didn't work. Although I was expecting the large language model with my prompt, it will pick the right tool to offer a coupon being the promotion representative. But it didn't work. So I might have to fix this. But for now, just pretend it works, give it offer the coupon. And then we'll go to the next step. And say the next step still like pick tool, but my role is going to still going to be now promotion still the same, promotion representative, prompt still the same, so how much, but I have a context now. So okay, I already picked the tool earlier step. The context is that I picked offer coupon as my context. So to code this, I will just copy this over to offer coupon. For prompt is copy this on how much are apples, and roll out going to be the same. And my system prompt is the same too. I got equal and refer. And I take, no, say it wrong one. Okay, select. And so then I'll take this and give it to my language model and paste it. Paste. Hard to do the paste correctly. Paste it, and doesn't let me paste. Why? Keyboard error. Okay, I copy and paste again. Okay, now I can paste. So this is a second time I actually engage the language model. So I was hoping it's going to say, hey, as this now you have to offer a coupon. You're going to look at database, but still didn't quite work. I'm disappointed because Gemini was working before I was developing this example. So the theory is that then now large language model is going to say, hey, next tool I want to use is lookup and reply. And this is when you have a new system role, maybe like respond. And then role is going to be you are a useful employee, or useful clerk, maybe useful clerk. And then, but then the prompt still the same. And then the content is going to be now actually looked up information. I use Apple. This is my keyword, and the search is result. And then this process will be the same. I'm gonna take the context over here, and then, okay. And then I have this. And then when I take all this, respond, or actually this says be short as well. Be short, and then, or maybe just one sentence. And then role is used for clerk, okay, and then this becomes a new prompt. You can give it to the language model, and then see, and I'll paste it as plain text, and then hopefully this time it's gonna be correct. And then so the Apple prices value signify common value, like, okay, so this is the final response that we give it to. But it doesn't, I'm disappointed it doesn't offer the coupon outcome. Oh, I forgot to paste. I should also pass this context over. So you can see that you should keep the memory in the context. So for interaction. So this is how I will update I just fix my code for my agent and to be able to pass the context across interaction. And then we'll say, and sales offering the best price with sales offering great price. Okay, so this is the right okay, so this is the right response. Eventually, your agent, our Gemini backed agent, will respond here and copy back to the let me see, paste. Where's the paste here? Is paste? Well, whatever. Okay, so this is I completed the agent loop. So you can visualize computers too. There were a lot more in the final total prompt template to your model going from RAG to agent. Also with agent, you have multiple interaction with the large language model before you actually respond back to the user. So a lot of different transaction with large language model depending on eventually before it respond to the user. So that's what happened in the background. Anyway, so I spent some time to go through this. I think I may spend a bit more time than I hope to have time to complete the rest. But I wanted to go down, appeal another layer to go down to the mathematical level and to see that why does the large language model hallucinate? Hopefully that most of you are still with me. And so the first is that I would like to show you that you might have seen this. This is a diagram from the transformer architecture. and only one side. Another thing is I turn it upside down because it follow the mass here. So at last, we have a last of there's a linear layer and softmax. And before we output some things called output probability. So this actually quite inaccessible for most people to understand. But I just want to focus on the softmax part. Hopefully, most of you, if you can use Excel, you can understand what's going on the rest. So what softmax does is that, well, just break down the last few steps. The last few steps is that the model is going to take all your token and give you this four number, or this four number is called model hidden feature. And so this is all you have for the transformer that actually does. And somehow you transform a token, say ETH as a token, into this representation. And then it has all the information you need to generate the next word. So next word you will actually take from vocabulary. And there's some process become really bigger. So we're not going to that process, but it's called linear projection. So it's going to become much bigger. So this will be all the word, all the different word in your vocabulary. So word 2, word 3. So you select this word depending on the number. So you like this value that has higher score. So you want to say, hey, I'm gonna say this value. So that's how what this linear does, this linear layer. And softmax is going to be the math we need to convert the score called logic score into a probability value. And probability value had to become between 0 and 1. So that's what we need to do. And the process, the math is quite easy. Hopefully it's not that hard. So one is that I want to take e to the z, but so it's easier for you to see 2 to, I'll use 2 to all this number to show you. So it's kind of like this. If you use base 2, but what I want to use is base e exponent. So I use exp instead to do the same thing, but instead we use 2. And then we sum them, sum this, okay? And then I divide all this exponents and by our sum. So this all of a sudden have this like distribution, and then we can see this distribution is actually high. Okay, so I will probably select this word to output as the next token. So that's how the decoding process works using softmax, the very, very end layers for transformer. Hopefully that's enough for today. But that's what's interesting is that how does it work? How do you actually select this? And I actually use a small example with a vocabulary only 5, who, where, why, what, how. So I repeat this process. How do we do softmax? I'll take the exp of the score and to do this. And then I would then the rest of it is the same. But then once you have this probability score, and actually we do not always pick just the maximum, because if you only do that, the model becomes really boring. So you will always send the same thing like robotic. So this is some random sampling process. We'll roll the dice depending on where the number is. For instance, in this case, it was ranked in such a way that if your probability if you roll a dice, say if I roll a dice, it will get 0.13. So this actually fall between 0 and 0.55. It's going to sample this word why. But if we happen to select the number to 0.61, and I will select the second word because between this range 0.59 and 79. But you can see down here, the where is actually very low probability. But you can still select it. One out of 100 chance. If you happen to roll a 0.99, you still select where. So there's one thing about the language model selection process for the word is you can always select even very low probability. And then there's some temperature. I think I'm gonna skip this temperature because I want to quickly get to one of the problem with this process is that, well, if we have a token, say ETH, and this is how the attention process means internally is that you were trying to, so we have this word called ETH, and then some hidden dimension, and it will become a query like this. Also 3 number very small. And with query, we'll say, if I have a word E, I want to find a food relevant to it. So I'll pay attention. So which one is food? So every single word in the sentence before should have a word. So for instance, burger is actually had the food. Is a food. So when you actually map this one to this one and this one chicken, both are food, you get high score. So that's how the math work. And if you examine this, it's just a dot product between the two. So I can implement dot product is actually matrix multiplication of whole this into this. Okay, so that you have this nice, and you have now you can see that for your 50-50 the chance to be paying attention to chicken and burger that both contain food. And then lastly is that, but this process, it forces the model to pick a choice. So what if you have all the previous sentences have nothing that's useful? For instance, in this case, my query like to look for something to eat. What do you eat? Some kind of food. And then none of this actually food. So if you take a dot product between the two, you get really low score. You still get very low score. Actually, sorry, I just proved the proof to you. This matrix multiplication and mult still get a very low score of all this word, but with the softmax, everybody is going to have very low probability of 0.1. And remember the process, we're gonna select one, and everybody has equally low attention still, but algorithm still will pay attention to them. You know what I mean? So everybody pay equal bad attention to everybody else. So mathematically, one way to combat that, so recently OpenAI received the open source model. They use this idea called sync token. What if we introduce a token just so ignore token, and I put some number to 1050. In this case, when no one else containing information of food, if you take a dot product, it actually could have and I select my query here. You can, sorry, one more time again. I select all my keys, tensor, and then all my query here. Okay, and then this value very high, but I'm going to be able to select ignore token. Your attention is going to select ignore token. By selecting ignore token, you actually get to ignore all of this. So that's one way that at the mathematical level, at this really deep level, that will come back the hallucination. Okay, and next, for the next 10 minutes, I think I now do have time to go through the rest of it now. It's because it'd be faster. This is probably the hardest part. You still survive, and you could just to see that. Hopefully, the idea is that dot product is what you need for calculating attention, and at the mathematical level down there, that because the fact that you just make some random choice, so that's why that you could use a self-consistency check, because every time you make a bad choice and it happens to be a different bad choice, so you can use self-consistency to be able to identify hallucination because of this phenomenon. All right, next we're going to talk about vector database at the RAG level. What's happening at the RAG level? So I'm going to show you a very quick emulation of how I would emulate a vector database in Excel to help you understand how vector database work, which usually driving a lot of RAG implementation. So first of all, we will have vector database want to store the document we like to put into our database. So we'll divide document into chunk. For instance, one of the chunk is that imagine this application. I want to talk about application of, we have this new employee onboarding process. We have that manual for new employee to read, but we'd like to build an AI agent to help the employee to understand the policy, but the AI agent cannot be hallucinating. You want to base on the true internal policy information the company has. So we got the chunk from the policy document. So there's this tool called sentence transformer. It's going to compute embedding out of this chunk. So the embedding is actually just a vector of numbers. So this is the example embedding. If we pick 8 dimension for our embedding vector, we get 8 numbers. So I'm not going through the transformer, sentence transformer, but the idea is that you have some process to turn your sentence into 8 numbers. So that to put both of them into a database, that's what we want to do. And to do so, we'll write this. This is an example from Pinecone, one of the big database. So vendor. So you will do something like, I'm gonna take my value is going to be this array. So I take this array, which is my JSON array. I already have it produced here. And if you see that it's actually live, if change it to 1, it's going to change back. All right. And metadata is that what is the chunk text on the store? So the chunk text is just the input here. This is a chunk to insert. So if you pass this JSON to your Pinecone database with index answer, so you can visualize the database, the table here. There's some table in stored ID and chunk text and some embedding over here. So I'll simulate the insertion. So there's going to be, I just type it. This ID is 10, and then the chunk is going to be this chunk. I go up to select my chunk. Here's my chunk here. This is a chunk. And I also select my embedding here. So I put in the table in this kind of structure. So my vector is here. I select this number and still here. Okay. So this is the story, actually emulating the story indexing process to index one word. And to retrieve from similarity is if we have a query code, say, what is a remote work policy? Imagine you talk to a chatbot about that. And want to retrieve this or some process to convert the embedding. But I'll turn to the vertical column because I want to do is also take a normalization. It turns out to search this database, we can compute cosine similarity. What I do is that I will need to first convert into actually using L2 norm. So that's those number actually hard to see here. So I could make it smaller so you can see the decimal. So these are smaller decimal numbers. And the L2 norm is the sum over square root of some square. So I have the equation here, so I'm not going to repeat. But it turns out if we take a square norm, L2 norm of all the embedding vectors, and then if I do a matrix multiplication here, that is compute similarity, cosine similarity between your input sentence remote work policy and all the document you have here, and and then we have this number. They have two actually kind of high number. So this is hard to see. Let me just make the font smaller as well. Okay, so now we have two of them, zeros. So these are pretty high cosine similarity between -1 and 1. So these are relevant with respect to the database. If you put the relevance rank, so I have number 1 here, number 2 is this one, and number 3 is this one. And so I will, and if I have the way to filter them, so what I do is I will do a filter and select a range to filter. I'll filter this one, and if the filter based on the ID smaller than 3. Oh, so one more time. Filter this array. I need to filter. Include is that if these are the rank, I said the rank smaller than 3. Okay, that's my equation. So I get these are top 3. So this relevant to top 3 chunks. Let me fix this. Top 3 chunks relevant to this top 3 chunks. That's how big the bus work. And then then with a reg, once I have that, I have a reg. If somebody used remote policy, so I can generate the reg right now here. So remote policies is this one, and context will be something I just retrieved. So I just select this 3 thing. So it's my context. So this is my reg using this example, and I will just copy this again into my large language model. I might have to run over time just a few minutes, 3 minutes, I promise. And then so paste the plain text. So this I'll complete my retrieval reg retrieval, and gonna generate all this text. Okay, just based on those information, and then hopefully this information is relevant to your work. Okay, so it's too much space. I couldn't paste into here. And last, I want to end with a very interesting. I think our only time to talk about re-ranker. One algorithm to make it even better is to when you respond to this. So one problem is that some of these sentences you retrieve might not be as relevant, but you still put it into your context when you give it to the large language model. What if there's a way I can put a score, for instance, this is the most relevant, this is less, and actually relevant from the retrieve and put some score, and the large language model will generate your response based on the score and put more words to describe the relevant one. So the idea is that when we rank those results, we are retrieving. So this is kind of ugly. Let me just to do this. Okay. And so that will use the large language model to do it. So we'll say test is rank this paragraph by how useful they will be summarized for the topic. And the topic is actually a prompt. So the prompt is, for this, I can select my prompt here. Remote policy, the same prompt. Remote policy and the document I retrieve are the same 3 things I have used earlier. So I just copy over here. And so this one, and then return the JSON array with score from 0 to 1 for usefulness. So similarly, I can emulate a re-ranker by, mouse is hard to use. Maybe use my mouse. Re-ranker. Take this as how the re-ranker works. You have this prompt template, and then you inject with the prompt, user prompt, and also retrieve document from your big database. You paste into a large language model, and then doesn't let me. One more time. I use my keyboard to select. This is my template, prompt template for re-ranker, and then I'll paste this. Paste as a plain text, and then this is how you'll hopefully get the right JSON file. So I'll copy the JSON file back to the large model. You return the JSON file, which I can paste here. I have some space. Actually, not enough space. Gemini just get more robust between the time I prepare this and remove this error. Okay, and then lastly, I can get a score. So I could update my prompt. Let's just delete. Maybe just copy a part of it. You can get the idea. Just copy this part. Okay. Paste. Oops. No, it's pretty. Okay, it's paste. Okay. One more time. Maybe copy this is easier. And now I'm just going to just add a few rows here. Add rows, insert rows. So I have enough space. Not overwriting my last finale step. So my paste here. Okay, so that JSON file. So now I could say is that I have a system prompt, which is just one sentence, for instance. One sentence, be short and be useful. Okay, and then prompt will be like remote work policy. Remote work policy. I just copied from earlier, but now the context is the same as before, but now re-rank. So these are the same context, but re-rank is that now have a score. The score is given from the JSON file. You have to write your own code to convert, to read the JSON file and put the score here, 1.1, 1.1, 0.5, and then the final step. Now you have this re-ranked, scored context chunks, and then paste to Gemini. Okay, this is very not doing what I want to do, but this paste as plain text, and then do it here. And now we finally get a response and you can see, if you read this response carefully, you'll realize in the last response, the paste. Does it let me paste? Copy, and paste. Okay, cool. So now you could see the final response actually put a lot more emphasis on the first two, and thinking about maybe the 0.5 is not as relevant. And by doing this re-ranking, you tend to be able to remove a lot of hallucination cases that you have a chance that just in case your RAG layer does an error retrieving, because the RAG retrieval, as you saw earlier, we use the cosine similarity. It does well sometimes, but doesn't. Sometimes it does let some irrelevant, just untrue things coming out. So it could be polluting your context. So use re-ranker to help with that. So anyway, so I did manage to finish how I wanted to finish and tell you going from really high level agent hallucination, can peel the layer off to see the math of LLM using some softmax, self-attention math that some of you might still be able to follow. And then at the end, we talk about re-ranker as the direct level and use this emulation you can kind of play with. So I found Excel a pretty cool tool to model agent behavior before you pick any framework to use. So there's you can just copy and paste the system prompt template into just a regular model and to test it prototype agent very quickly. Anyway, so that's all I have today.